data when encoding is really rough. We have here an uncompressed audio data. This is the time axis. This is the frequency axis, and the the hue value of the pixels shows the intensity of this frequency. So we have here near silence and some, well, sounds in here. And after decoding, it's gained a lot of distortion. So 96 kilobits is a bit small for this kind of signal. We also see that we have a cutoff frequency here. The codec just throws away higher frequencies. Yeah, any questions to the encoding? Okay, then let's proceed with the packetizing. Again, let's have a look at what components generate the stream. We have for every program a video encoder, audio encoder, and a reference clock. The reference clock is needed to align the audio data to the pictures so that, well, the sound comes synchronous to the mouth movements. And, well, this takes a lot of, well, twitchery with datas and clocks to have this synchronous and not have the speaker talk when he's silent again. Then, well, we have another channel. Here we have two audio encoders. This is, for example, on Arte, on Astra. They are doing a German and a French audio subcarrier. Pro7 does German stereo sound and AC3 surround sound. So we can just add an arbitrary number of audio streams. We have several multiplexers. One is inside every encoder, and we have the final multiplexer which does combine all the additional data, the PSI tables, the electronic program guide, perhaps some teletext channels, and, well, we can do IP data service as well. Well, in fact, we can add any data stream we have to this DVB signal stream or transport stream. This is the packet format. Every packet is 188 bytes long. Well, this seems to be quite a random number, but in fact it's not. It's 4 ATM frames if you count the ATM adaptation layer as well. This comes from the fact that most transmitters are not located at the studio where the stream is created, but somewhere on a hill or on a mountain in the Alps, and you use a normal telephone carrier connection to transport the transport stream to the transmitter. And, well, using the ATM network for that is an obvious choice. So somebody thought this would be a good number. Every packet starts with the sync bytes 47 hex. This is everywhere. Well, you can think about how much bandwidth is lost in the sync bytes alone if you do some 10,000 packets per second. You can do a lot of things in that. But, you may not change the sync bytes because the receivers won't lock on the signal. A sad thing. Then we have the PID, the packet IDs, which help the demultiplexer to identify the original streams. Every original stream has a unique ID, and the demultiplexer just does comparing, does compare the PID it wants to receive with the PID of a received packet, and if they match, the packet is passed on, otherwise the packet is just dropped. It's like the MAC address filter in your Ethernet card. Well, but it doesn't address the machine. It tells the receiver this is sound for program 3 or something like that. Then we have the clock reference field. It's not in every packet, but it's quite common or frequently transmitted, and it's needed to align the sound to the video signal. And after that, we have the payload, normally 184 bytes for each frame. This can be less if more header fields are added. The header contains a flag field which tells how many header fields are present, and then the header grows and the payload area gets smaller. And well, the transport stream frame ends here, but the standard also allows 204 byte packets, and the last 16 bytes then carry the Reed-Solomon error correction code. This is needed to correct reception errors later on at the receiver side. Well, normally you don't receive these bytes. They are already used when you get the packet to work with it, used while compensating for reception errors, and then just cut off the packet. So, next step. What data is inside the stream besides of video and audio signal? Well, mother of everything is the program allocation table. It has the PID 0, and from there the programs are referenced. So the first reference goes, well, to the network information table. This has a special meaning. And then every program has a program map table. Inside the program map table is a list of what streams belong to this program. Well, and obviously the PIDs needed to get in touch of these packets. So the program map table has a list telling the receiver, let's say Pro7 has video PID 101, audio PID 102, teletext something, and well, that's the list, and the receiver then lets you choose from several audio streams, perhaps, if the software does this. The network information table tells the receiver about the names of, or the name of the network, and well, several IDs, which help the receiver to, well, the idea is that the receiver has the chance to detect if you are watching the same program over several different channels, well, frequencies. So the receiver can say, well, Pro7, I know that one. I used to receive this on another channel, but now I update this program entry in the list. That's a lot of information in the network information table. Also, there is a list of other receivable frequencies. So here the idea is that a receiver that can receive the network information table can start spidering the channels without doing the long frequency scan. Just find the first one and then try the other ones referenced in the network information table. And then the stream also contains several tables which are not referenced but need to be there with fixed PIDs. The first is the service descriptor table. This carries the program names. Well, I don't know why the program names are not here in the program maps, but, well, somebody decided that way. Then we have the event information table. The event information table isn't a table, it's a huge data stream carrying the electronic program guide. So why the electronic program guide isn't a distinct PID for every program, I don't know either. Doesn't make any sense to me, but well, we have to live with it. And then we have a rather easy table, that's the time definition table. It's just the time of the day in universal time coordinated. Well, DVB in binary isn't fun at all. It's got a lot of length bytes and attached data after that. So DVB mostly is one big buffer overflow. If you want to own a set-top box, it takes you 5 minutes, I guess. While writing the generator for the tables for the Congress TV, I just owned our test receiver. It crashed so hard we had to remove power. Switching on and off didn't work anymore. I guess most of the receivers out there are prone to hacks, so perhaps we now know what the next conference lecture will be. So yeah, it even gets better. Most set-top boxes support online firmware updates using the... Okay, fantasy is here, I know. Okay, Thomas, now it's your part. Thank you.
So, hello everyone. I'm going to talk about what happens to the data stream after being fed through the multiplexer into the modulator. The purpose of the modulator is to modulate the data stream onto a carrier wave. This is what has to be done to transmit it over the air. First thing, here is the block diagram of the modulator. There's lots of complicated stuff in there. I'll just go through some of them. Basically, the gray parts are the channel coding. There is some energy dispersal to generate a pseudo-random looking signal. This is needed for the HF signal having a nice spectrum. It's just to have a nice HF spectrum. You have several layers of error correction. There's a Reed-Solomon coder working on byte level, some interleavers. There's an FEC coder working on bit level. Those two match pretty well because the FEC coding works on bits and corrects errors which are randomly spread, also known as noise. And noise is known to happen pretty often in transmissions over the air, while the Reed-Solomon coder corrects block errors. For example, if someone walks by your antenna or a bird flies by your satellite dish or something, this is corrected by the Reed-Solomon coder. If there's snow on your satellite disk, which just adds noise, this is corrected by the FEC coder. There are some interleavers to spread errors around, but that's not too important. We need symbols, interleavers, constellation mappers. We will come to them soon. There's a Fourier transformation which does the OFDM modulation, which I will explain later. We have some filters which are needed on the HF part to prevent usage of the adjacent channels, because you probably only got one channel and you shouldn't disturb the others. Have I mentioned we will build a DECT hacking thing next year to shut the phones up? Sorry. Okay, so that's basically the block diagram of the modulator. Will come to modulation. For modulation, you need a carrier wave. This carrier wave probably looks something like this. It's a plain sine wave. And what you want to do is you want to impress information onto the sine wave. There are three ways to do that. The first way, the most basic one, is the amplitude modulation. It was basically invented more than 100 years ago, and it's still used today in Morse code, for example. Morse code is the most basic form of amplitude modulation. Just switch the transmitter off and on. Amplitude modulation uses intermediate steps, but that's what it does. Then there's frequency modulation. You can change the frequency of the carrier wave. It's also shown here. It's pretty intuitive. And the most unintuitive thing is phase modulation. You just change the phase of your carrier wave somewhere in between, which leads to some jumps in the time diagram. The interesting thing about that is that frequency modulation and phase modulation are correlated, so you can only use one of them. If you do frequency modulation, you also modulate the phase in some way. Otherwise, if you modulate the phase, you have to change the frequency. Other than that, the amplitude modulation is orthogonal to that. You can use amplitude modulation and frequency modulation on the same signal at the same time without disturbing each other. except in some special cases where the amplitude gets 0, but you